Hello and welcome to the latest Our Past, Your Future STEM encounter. Today we have Kέllη Kúsi, who's a scientist, going to tell us all about her work.
So hello everyone, welcome to our assembly. Today's special guest is Kέllη Kúsi, and she is going to be telling us all about her job and answering some of your questions. So hello, Kέllη.
Hi everyone. I wish I was there with you, but I'm glad to meet you, to meet you either way.
Okay, so have you always wanted to be a scientist?
Well, no, the short answer is no. I was always an art person. So as a younger child, I used to do a lot of dancing, ballet, I used to play the violin. And so I wanted to do something like that. But I also kind of wanted to keep it like to myself, something a bit more private. And you know, people say make your hobby your job, but also, you know, you need to have hobbies separate than your job. So I thought I would do something that contained that. But because I'm also quite a structured person, I thought I wanted to be an architect, actually. So in order to be an architect in Greece, you need to take a lot of design lessons before actually going to university. And I did a lot of like structural design and abstract design. But then I met this teacher when I went to high school who was a chemist and introduced me to chemistry. And wow, this was actually a different kind of art. So it allows you to be creative because you get to ask so many questions and get answers about things that like we are chemistry, right? So it is something that affects all of us in everything that we do and everything that we are. And also, I was also always one of those kids that, you know, ask all the questions, but I know that a lot of my classmates didn't, and a lot of our teachers didn't properly answer those questions. So I wanted to be the one to ask the questions, but I also wanted to be the one to answer the questions. So that's why I decided to be a chemist and a researcher. It allows me to be creative, but it also gives me structure and rules.
So what did you need to do to get there?
All right, so I'm from Greece. So I did my undergrad's bachelor's degree in chemistry in the University of Patras. And then that's where I also did my master's on clean energy production. And then from there on, I continued and did the PhD in energy production from different kinds of fuels in the chemical engineering department. I worked for a company that specializes in fuel cells. And I then wanted to do something more because, like I said, I want to know everything. So I wanted to do something outside my country, and that's why I came to the UK in 2017. And specifically in the University of Newcastle. I stayed there for 4.5 years. And then in 2021, I moved to the University of Surrey and I became a lecturer of chemical engineering, where I work on different kinds of materials for energy conversion applications.
Lovely. Okay, so what do you do as a research chemist then?
Okay, so I am no longer a research chemist, I would say. Like I mentioned before, I'm a lecturer of chemical engineering. This has two aspects to it. The first thing is I get to teach university students of chemical engineering how to become researchers and engineers. And the other part is I am head of a group. So I have research chemists and chemical engineers working for me. So what a research chemist does. So a researcher generally tries to answer questions that would be important and of great impact for all of us. really. And they do this by either working in a lab, or actually today they can work through a computer and do experiments to verify or not really all these questions that are burning questions for all of us. We specifically work on energy application, which is more on hydrogen production, and we're trying to see how from using different fuels we can have a more circular economy.
Okay. And just for our younger people, so hydrogen is a type of gas, isn't it?
Yes, yes, it is.
So our next question is, what is a sustainable fuel and why are they important?
Okay. So a sustainable fuel is an alternative to petroleum. And this is, for example, this takes into consideration also how this is produced. Like, for example, how much water was spent in order to produce this fuel, and how much land was actually used to produce this fuel, which is very important because we know nowadays there are, we need to take into account how people are being fed, like how water is used in a consistent for all of us way. Examples of sustainable fuels can be, for example, vegetable oil. So the oil you cook can be used directly in burners and be a fuel. Another thing that it can be, you can use CO2, which is carbon dioxide from the atmosphere, and actually use hydrogen, like we said before, and put them together and produce kerosene, which kerosene is a fuel for planes, right? And the other thing is, when you use CO2 and hydrogen to produce kerosene, because they are clean to begin with, you don't have the other nasties that they produce, the fuels produce when they're being burned, like different particulates in the atmosphere. So it's a double win, I would say. So I think that leads quite directly to why they are important. I think they are important because they allow us a more hopeful, let's say, future. We, for example, take CO2 from the atmosphere, which is a greenhouse gas. So it is important to remove it from the atmosphere as much as we can and not emit anymore. And we use it to actually move, to get on a plane and go someplace. And that helps us have a more sustainable future. And that's why I think they are so important. In the lab, we actually work on different energy applications. For example, we treat gases that go out of exhaust of a vehicle's exhaust. We make those fuels, like we said. We make chemicals like methanol, which is used in a lot of pharmaceuticals. We test different properties of the materials, and we also try to test fuel cells, which are used in, the new cars, for example.
Cool. So it definitely sounds like something that is really going to help us protect the environment.
Hopefully, yes.
So you've been working on lots of these different things. Can you tell us a bit more about some of the things you've been working on, please? Okay.
I'm going to try to make it very simple to begin with. Maybe too simple, but I work on a field called catalysis. And what we do is we try to make the best catalysts that we can. Now, what is a catalyst? Think of a squirrel, right? And that squirrel needs to make something to eat. But he knows that he needs to transfer his nuts up the hill in order to go to the fire and make that kind of food that he wants. But our squirrel might be a bit smarter than that and knows that there is a way through that hill that will allow him to just kick his nut and not just carry it on his back and go faster to that food plot. So that's what the catalysts do, pretty much. So catalysts allow you to speed up what you want to do. For example, if you have a hydrogen molecule and an oxygen molecule and you put them side by side, they will never make water. But if you put a catalyst next to them, you'll have water in like milliseconds probably. They cannot make you do something that was not possible to begin with, but they can do in very, very, very short amounts of time something that could take millions of years to happen. So that's what we do. We try to make these catalysts the best that we can. So a catalyst in the laboratory looks like your picture here on the left, and it's usually like a powder or a small pellet. And what you can see here, it's actually the way your car catalysts look like. If you go under your car, you can see exactly this thing. So this is the outside cell, and in here there is this powder that allows you to convert those nasty gases that come out of your car and go as something a bit more benign in the atmosphere. Now, this powder has the size of, its grain of this powder has the size of about hair, like that's how small it is. But this whole grain is not active, and your active ingredient sits on top of this powder, on top of the surface of this powder, and it's about 10,000 to 100,000 times smaller than your hair. So as you can see here, that's what we do in the lab. We're trying to control this and make the best out of it. And we have a new method now, which I'm really proud of, that we are able to fully control these small particles that are very active, and we can make circles, we can make round particles and square particles, and we can even make hearts, if you can believe it.
So how do you actually create and test fuels then?
So if you think about what I said before, is we make this material, which is the catalyst, and then we need to force, for example, like I said before, the carbon dioxide from the atmosphere and the hydrogen to come together through that catalyst and flow through that catalyst, because they're gases, under some high temperature or pressure conditions, and this actually creates the fuels. So I can show you here, like these are how the testing setups look like in the lab. This is something that I've created myself. And this is something more like engineering, I would say, like a chemical engineer would do. And you can see me, like for scale, working with that on the laboratory. Here, I wanted to show you how this actually looks like in the industry. So what the top image is an actual design of an industrial unit. And under it, you can see how this assembly unit looks like. And you can see someone for scale actually there. So what we have this huge like barrels that you have probably those, for example, the CO2 and hydrogen that we mentioned before. You have your catalyst. These are high pressure and temperature, and at the end you have big complicated, I would say, equipment that actually tries to measure how much of the original thing that you put in was converted and to what. Did you actually make kerosene, or you made something else that you don't like? So that's how we test the fuels, if we did anything really, and that's how we make it. And from there on, it can be transported directly to like a refuel station, or depending on the fuel that you're making actually.
Fantastic. So the last questions that people sent in were, what do you like about your job, and are some bits of it hard?
Okay, I'll stop sharing so that I can properly see you. So, oh dear, there are many things that I like about this job. I practically feel like I can have a real impact, and I know it might sound cheesy, but change the world, because for starters, I get to educate all of you, right? All of the new people that want to be scientists and want to be engineers, which is amazing, because I really want to inspire you and show you that this is something that, you know, is worth doing, and it's amazing. And on the other hand, because I'm head of a research group and I have my students working on these actual questions and these actual problems, it's also so exciting trying to find a solution to our everyday problems. And, you know, the earth and the environment, they're our home. And this is the only one we have at the moment. So it's very exciting to try to work away of all of us living a better life. Now, bits that are hard. I define that this job is a bit of a unique job. I know that everyone pretty much will say that, but I think it is, because it is a structured job, but also at the same time, it's very free, which means that whatever your questions are, they won't be answered during 9 to 5. But what you create is your baby, right? So that means that your mind is constantly there because you want to answer the next question and the next question. So this is a bit tricky to stop thinking about it. And the other thing is that you might be doing a lot of experiments for a long time, and then you never get what you want, right? Which are still answers. They are still answers and they are still results. But, you know, we all are like, fingers crossed, this will work, and it doesn't. So you need to come to terms with the fact that, you know, this is part of the job too.
So you have to be quite resilient then, because
yes,
in the news, you'll hear about the amazing discoveries that scientists make, but you don't hear about all of the effort that gets put into actually getting there.
Of course. And if you think about how many like different kind of industries a research chemist or a chemical engineer can go into, they can make like the vaccine, right? That's something that we are all talking about at the moment. But how many people worked for this? And because this was done quite, you know, quite soon, since the pandemic started, for example, we all think it was very easy, but it was not. There was like so many people working on it, and it was based on work that was done for years and years and years. They did not just wake up and make a vaccine. And that's the same for energy applications, or for example, food science. We need to be curious so that we ask the right questions or the wrong questions, but we ask questions. But we also need to be persistent and resilient in order to not give up.
Brilliant. Well, thank you very much for coming along and taking part in our assembly. And I'm sure that our students will be really interested to find out your answers. So thank you.
Thank you very much for having me. I hope that I just answered just a tiny bit of what you have in mind about research and chemistry and chemical engineering.
Thank you to all the schools for sending in such fantastic questions, and thank you, Kelly, for coming along to answer them.